Hi, I'm Ben-Yaakov. The title of this presentation is Definitions of Inductance, AC Inductor, and DC Inductor. The objective here is really to correct some misconceptions regarding these definitions. So let me start with the inductance. The formal definition of inductance is N phi over I. Now this relates to a case like this, for example, in which we have a ferromagnetic core of some permeability. Then we have a number of turns, N turns, and we have a current going through this turn, and this excitation causes a magnetic flux within the core. We assume it is confined to the core, and the definition is N phi, N number of turns, phi is the flux over I. There's another way to define the inductance, and this will be by the, state equation. V is equal to L di dt. And by defining L here, we find that L is equal to V over the derivative of the current, the change of the current. So this will be seemingly a different way to define inductance. However, both of these definitions really emanate from Faraday's law. It states that V, the induced voltage, is equal to N d phi dt, phi, a change in the magnetic flux. Now, phi by itself can be expressed in this way. What we have here is mu, the permeability, cross-section area here of, say, of the core, and number of turns, I is the current, and Le is the magnetic path length, okay? Now, Ni over Le is the magnetic field, times mu is the magnetic flux density, and times Ae is the magnetic flux. So this is just the expression for the magnetic flux. So if I put this expression here in this derivative, everything here is constant except for the I, so I end up with this expression, N square Ae mu over Le times di dt in this case. This is the derivative here. And as you'll notice, okay, we see that L actually can be also expressed as N square Ae times mu over Le. This is really heavily related to the structure, that is the cross-section, the magnetic path length. Okay? Now, rearranging this by taking out N divided by I and multiplying it by I, we end up with this part here, which is exactly phi, the magnetic flux. So therefore, we find that V is equal to N phi over I, so this is this definition here, L, di dt. So let me just summarize that the definition of L is really a consequence of Faraday's law. Now, if we look at the expression for L, okay, N square Ae mu over Le, there are parts here which are structural, the cross-section, Le, but then there is part which has to do with the material. This is the permeability of the core. Now, ideally, permeability is a constant, but in practice, the cores that we are using, ferromagnetic cores, are non-linear. And here's a typical BH curve of, say, a ferrite core, and it's non-linear, and we cannot operate it to the end. We have to constrain ourselves. And then we can actually define a number of permeabilities here. For example, we can define a local permeability or a derivative permeability, or we can define a total permeability. Suppose we are here, then the total B over total H is the total permeability. Now, each one of them leads to a different type of inductance. This would lead, here's the definition of inductance, this will lead to a differential or local or small signal inductance. Now, will be defined by actually the derivative, the change in phi divided by the change in I, or based on total permeability, we can define a total inductance, and in this case, we have N phi over I. This is the classical definition. But this is only for this case. Now, in fact, the most useful inductance that usually is used in engineering is the derivative or local or small signal inductance. For example, a manufacturer are giving us a curve like this, inductance as a function of the DC passing through the inductor. They are not saying it, but this is the derivative of small signal inductance. The way it is measured is by injecting DC, then superimposing an AC component, and then measuring, of course, the voltage and the current, and from which you can get the inductance. And this is the derivative or local or small signal inductance. So let me summarize the points that I've stressed above, that there is no one definition of inductance, and that the most useful inductance is in fact the differential inductance. And for that differential inductance, this definition does not hold, it's incorrect. Let me move now to the definition of AC inductors and DC inductors, which are related, but it's not the same issue, of course. We find in, say, LinkedIn posts and YouTube videos, and in fact in papers, a reference to AC inductor and DC inductor, okay? Now, DC inductor is understood as an inductor that need to accommodate a DC current, on which, of course, an AC or ripple component is usually built. And in this case, it is generally recognized that you need a gap, an air gap, in the core. On the other hand, there is a reference also to AC inductors, in which there is no DC component, so there is only AC, that is, the average is 0. And it is claimed that AC inductors do not need an air gap, and that their design is different from that of a DC inductor. Well, this is a big mistake, and here is the reason. Energy stored in an inductor is Li squared over 2. Now, the size of the inductor is proportional to the stored energy. And energy is, of course, proportional to I squared, so the current is very important in storing energy. Now, without a gap, ferromagnetic core cannot tolerate large current. And the reason is, again, because that cores are built on ferromagnetic material, which is nonlinear. It has a limit at saturation. And so typically it will start with a sharp slope with a high permeability, and then it'll go into saturation, like a ferrite core. Now, if we have to limit ourselves to a given magnetic flux density, this will limit the magnetic field that we can have within the core, and magnetic field is, of course, a current, proportional to the current. So, in the case of a core without a gap, we are really restricted here. On the other hand, if we add a gap, the permeability drops down, and consequently, for the same magnetic flux density, we can go to a much higher magnetic field, and therefore a much higher current. The bottom line is that with a gap, the core will be smaller than a core without a gap. There's no question about that. Or an inductor with a gapped core will be smaller than an air inductor. That is, a core with a gap is presently the best solution available. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it of interest, and perhaps it will be useful to you in the future. Thank you very much.